While much of the world races toward faster production and louder innovation, Japan has spent decades pursuing something far more difficult to master: perfection without compromise. This is the heart of the Shinkansen N700S factory, where one of the world's most advanced high-speed trains is born. A machine capable of traveling at 300 kilometers per hour, yet quieter than a normal conversation and smoother than most cars at highway speed. This level of control is not accidental. It emerges from a culture that refuses shortcuts, questions every assumption, and verifies every step with science and discipline. Hit the subscribe button and motivate us to bring you even better quality content. Today, we uncover the process that transforms raw aluminum into controlled motion and why this factory remains the benchmark the world quietly studies. Number 1. Raw materials. The Shinkansen N700S begins as specially formulated aluminum alloy panels and structural frames designed to balance lightweight strength with durability for high-speed travel. Before any production step, each shipment undergoes rigorous testing for tensile strength, fatigue resistance, and heat tolerance because high-speed trains face constant stress cycles that ordinary metals cannot withstand. Any batch that fails even one test is rejected immediately, no exceptions. Once approved, every panel is digitally labeled, logged into a traceable system, and stored in climate-controlled zones to prevent warping or corrosion. Advanced measurement systems scan for microfractures, surface defects, and precise thickness tolerances, ensuring every part meets strict engineering criteria. This early verification protects structural integrity once the train is in motion. In the Shinkansen process, excellence begins at the gate, where raw materials must meet exact standards before a robot or human ever touches them. Only material that passes every check moves forward, forming the reliable, durable foundation for a train that will safely and smoothly glide at 300 kilometers per hour. Number 2. Car body assembly. After materials pass inspection, the process of building each train car begins with absolute control over structure and alignment. In dedicated assembly zones, high-precision robotic arms position large aluminum frames with millimeter-level accuracy, guided by advanced laser projection and measurement systems that constantly verify reference points. Parts manufactured by companies like Hitachi and Nippon Sharyo are engineered to exact tolerances so they fit perfectly without gaps or misalignment. Throughout assembly, digital sensors monitor position, angle, and distance in real time, allowing engineers to catch even microscopic deviations that could later cause vibration or increased drag at high speeds. This stage is never rushed. The focus is on precision, repetition, and discipline, with quality checks after every sub-step. Before the body moves on to welding, every frame is measured multiple times and confirmed to match design specifications. This careful construction ensures the car will be aerodynamically stable and structurally sound, forming the backbone of a train that travels smoothly, quietly, and efficiently across Japan's high-speed network. Number 3. Welding. Welding, the Shinkansen N700S is far more than joining metal. It is precise metallurgy in motion. Aluminum, chosen for its light weight, reacts differently than steel, requiring exact temperature control, precise pressure, and a contamination-free environment to form bonds capable of handling continuous high-speed stress. Robotic welding arms follow programmed paths with smooth, consistent motion, repeating the same weld thousands of times with perfect accuracy. But visual inspection is never enough. Every seam undergoes X-ray and ultrasonic scanning, allowing engineers to see inside the metal without cutting it open. Even microscopic flaws are unacceptable. Any detected defect triggers immediate rework or rejection. The welding process also accounts for thermal expansion, ensuring the metal contracts without warping as it cools. Structural integrity here is absolute because at 300 kilometers per hour, even tiny deficiencies could compromise safety. These systems reflect the Shinkansen philosophy. Perfection is engineered, measured, and verified, never assumed. Number 4. Aerodynamics. Aerodynamics on the N700S is not cosmetic. It is critical performance engineering. Before paint is applied, each car body is polished to near-perfect smoothness, minimizing drag, turbulence, and high-speed wind noise. The dual Supreme wing nose design reduces air resistance and suppresses the infamous tunnel boom, the pressure wave created when a train enters a tunnel at high velocity. Engineers combine laser measurement systems, computational fluid dynamics, CFD, and real-world tunnel testing to ensure airflow remains laminar across every surface. Each curve, angle, and contour is iteratively adjusted to optimize efficiency, stability, and energy consumption. Even subtle protrusions or misalignments are corrected because aerodynamic imperfections at 300 km per hour amplify vibration, energy loss, and passenger discomfort. From the nose cone to the roof and sides, aerodynamics drives every design decision. In the Shinkansen, physics shapes beauty engineering. Precision governs performance, not aesthetics. Number 5. Painting and coating. Painting the N700S is a precision process where engineering meets aesthetics. Work is performed in sealed clean rooms where dust, humidity, and air pressure are tightly regulated to prevent contamination. Each car receives multiple layers of specialized coatings, applied with micrometer level accuracy, creating surfaces that resist corrosion, abrasion, and temperature fluctuations. Beyond protection, these coatings improve aerodynamic stability at high speeds by maintaining perfectly smooth airflow over the car body. The train's signature blue stripe, a visual hallmark, is applied with robotic precision to ensure uninterrupted alignment across all cars. After curing, every surface is inspected under powerful lighting and scanned digitally to confirm uniform thickness, color consistency, and reflective quality. Even tiny imperfections are corrected immediately, because at 300 km per hour, surface flaws affect drag, airflow, and energy efficiency. This process demonstrates how the Shinkansen blends durability, performance, and beauty, ensuring the train looks impeccable while performing flawlessly over decades. Number 6. Bogie and suspension systems. The true heart of the Shinkansen's motion lies in its bogie system, the complex undercarriage that connects the train to the tracks. Each bogie houses electric traction motors, advanced suspension components, and shock absorbers, and is tested independently under full operational loads before being installed. The N700S features lighter, more robust bogie frames, optimized weld points, and integrated air tanks that improve structural integrity while reducing overall weight. Advanced suspension design reduces vibration and noise, providing passengers with a smooth ride even through tunnels and curves at high speeds. Alignment is verified to the millimeter to prevent wobble or instability, while precision engineering ensures long-term reliability and reduced maintenance requirements. Every component is stress-tested, simulating years of wear to guarantee safety and performance under extreme conditions. In a Shinkansen, speed alone is meaningless. These systems ensure control, comfort, and efficiency, translating engineering discipline into a ride that feels effortless and stable at 300 km per hour. Number 7. Innovative safety systems. Safety in the Shinkansen N700S is engineered to a level few high-speed trains in the world can match. Every train car is equipped with redundant braking systems, meaning if primary brakes fail, secondary systems automatically engage without delay. Advanced earthquake detection sensors can sense initial tremors and trigger emergency braking before passengers even feel the vibrations. Fire detection, smoke suppression, and emergency lighting are fully integrated and continuously monitored by a centralized control system. Engineers run simulated disaster scenarios in software before trains ever leave the factory, ensuring every subsystem responds in milliseconds. Redundant power circuits and backup batteries ensure the train continues to operate even under severe electrical failures. Every emergency system is stress-tested repeatedly, proving that at 300 km per hour, the Shinkansen prioritizes human safety above speed. Here, engineering is not theoretical, it is repeatedly verified under extreme conditions to achieve zero compromise. Number 8. Digital systems. The Shinkansen N700S is as much software as it is steel and aluminum, a rolling supercomputer on tracks. Thousands of sensors distributed throughout the train continuously monitor speed, vibration, temperature, electrical load, and structural integrity, feeding real-time data into control systems that anticipate anomalies before they escalate. The train's advanced traction system uses silicon carbide (SiC) components, reducing energy loss and enabling a more compact, efficient design. A lithium-ion battery system allows the train to operate at low speed during power outages, providing extra safety and redundancy. All digital systems are synchronized, and software is uploaded, verified, and locked, forming a single, integrated network across all cars. Engineers simulate emergency scenarios, from sudden power loss to earthquakes, testing response times down to milliseconds. Every subsystem must respond perfectly because at 300 kilometers per hour, safety is proven through data, testing, and precision, not assumptions. This digital architecture turns every Shinkansen into a self-aware, high-speed machine, where engineering intelligence guides speed, stability, and passenger safety. Number 9. Energy, efficiency, and sustainability. The Shinkansen N700S is designed to minimize energy consumption while maintaining maximum performance. Its lightweight aluminum frame, aerodynamic nose, and low-drag body all contribute to reducing power usage at high speeds. The train utilizes next-generation traction systems with silicon carbide (ESIC) semiconductors, which are more efficient than traditional silicon, converting more electrical energy into motion while generating less heat. Regenerative braking captures energy normally lost during deceleration and feeds it back into the power system. Climate-controlled interiors are optimized for energy savings, with intelligent LED lighting and zoned air conditioning adjusting to passenger load and temperature. The N700S also supports renewable electricity sources at depots, further reducing carbon emissions. Efficiency is engineered into every system, proving that high-speed performance and environmental responsibility can coexist seamlessly. Number 10. Interior engineering. Inside the Shinkansen, comfort is engineered, not improvised. Layers of noise reduction materials are strategically installed to isolate vibrations and absorb sound, while ultra-sensitive measurement systems detect frequencies imperceptible to the ear but felt by the body. If tolerances are exceeded, engineers adjust insulation, support structures, and wall panels until standards are met. Seats are ergonomically designed, with integrated power outlets, USB ports, and adjustable lighting, enhancing passenger convenience on long journeys. Climate control systems maintain stable temperatures and subtle airflow patterns, preventing drafts or hotspots. Cabin lighting is calibrated to reduce fatigue, while emergency systems are integrated seamlessly without interfering with passenger experience. Even small details, like the positioning of handrails and luggage racks, are optimized for safety and ease of use. The Shinkansen interior is a controlled environment, where every vibration, sound, and airflow is managed to deliver a quiet, smooth, and comfortable journey from the first car to the last. Number 11. Passenger experience. The Shinkansen is not only about speed, it's a masterclass in passenger experience. Interior noise levels are kept below 65 decibels, quieter than a conversation in a living room, thanks to vibration isolation and sound-absorbing materials. Seats are ergonomically shaped, fully adjustable, and designed for long-duration comfort. Intelligent cabin climate control maintains optimal temperatures while ensuring subtle airflow patterns that passengers barely notice. Luggage storage, lighting, and digital displays are all integrated into the interior design with precision. Even subtle movements from track vibrations are absorbed by the advanced suspension system, ensuring a smooth ride through curves and tunnels. Wi-Fi, power outlets, and quiet zones are all engineered into the cabin without sacrificing safety or structural integrity. Every detail is calibrated so passengers travel in comfort without realizing the complexity working silently beneath them. Number 12. Final testing. Final verification is where technology and human expertise converge. Before leaving the factory, each N700S undergoes exhaustive testing. Motors are run at full operational speed while the train remains stationary, while torque, vibration, heat generation, and braking performance are monitored in real time. Exterior surfaces are examined under intense lighting to ensure aerodynamic precision. The train is also tested for emergency responsiveness, including simulated power loss and automatic braking execution. Only then do veteran engineers walk the entire train, using decades of experience to catch subtleties that data alone might miss. This step ensures that every component from structure to system is ready for service, reinforcing the philosophy that engineering excellence is verified, not assumed. Number 13. Advanced maintenance and monitoring. The Shinkansen N700S doesn't just rely on upfront engineering. It's designed for continuous monitoring and predictive maintenance. Thousands of sensors track vibrations, motor performance, wheel wear, and bogie alignment in real time, sending data to centralized monitoring systems. Predictive algorithms analyze trends to detect issues before they become critical, reducing unplanned downtime and increasing operational safety. Components like brakes, wheels, and traction motors are scheduled for maintenance based on actual usage and wear. Even interior systems like climate control and lighting are continuously monitored for anomalies. This proactive approach ensures that trains maintain consistent speed, smoothness, and reliability over decades of service. Maintenance is no longer reactive. It is a sophisticated, data-driven operation that keeps the N700S at peak performance.